tonight I have a function that is defined via summation. They call it arithmetic function, mapping from the natural numbers to the natural numbers. Now I'm just going to write this kind of shorthand. What I've listed here are all the divisors of 6, and you can use this vertical bar here to indicate that these are the only divisors of 6, namely 1, 2, 3, and 6. All right. Now this other guy right here, this is the tau function. It counts the number of divisors, and I'll just write down tau at 1. I'll just make it like a t. Tau at 1 is 1. 1 has 1 divisor trivially, right? Okay. Tau at p, a prime number. And like I say, you can define the prime numbers via these arithmetic functions if you want to, some of them at least. You could also define it, the Euler-Phi function. It's always one less, you know. But this is equal to 2 because p is defined to be the integers that have 2 positive divisors, namely 1 in themselves, all right? T at p squared. It's pretty quick. It's pretty easy to see what's happening here. This is equal to 3. All right, and in general, t at p raised to the k is k plus 1. All right. Now, just right here for the, why is this equal to 3? Well, you can write down the divisors explicitly. 1, p, and p squared are the only divisors of p squared. Otherwise, p would not be. If there were any others, p wouldn't be a prime number. Okay, it's pretty straightforward. Okay, so let's move along. Now again, we've defined this function of n that ranges through all the divisors of n, and then it counts the divisors of each of those divisors and then sums them up. Okay, that's what this means. Okay, so we want to show that this function, as we've defined it here, f evaluated at p raised to the k is k plus 1 times k plus 2 over 2, the quotient. Okay, so let's get busy. Now I've done most of it for you folks. You can see here the divisors are for p raised to the k power. P raised to the k power. I call that p of k for some reason, but it's p elevated to the kth power. The divisors of p to the k are 1, p squared all the way out to p to the k. And it may be useful right here to write in just to make sure there's any loss of clarity here. K minus 1 precedes k, right? All right, so that would be the term right in front, right here, okay? So that's where this k comes from. You see, as you march across here, 1 has 1 divisor. Any prime number has 2 divisors. Any prime number squared has 3 divisors, and so on like this, okay? Now, the good thing about this is that this is very well known. This is the famous triangular number sum. And this is certainly equal to k times k plus 1 divided by 2. Okay. That takes care of 1 plus 2 plus 3 plus all the way to k. All right. Now let's go ahead and write k plus 1 next to it. There's a sum here. So we're just dealing with a common denominator problem here. In the manifestly, that's 2. Okay, so you could write this as equal to, I think I have room here, k times k plus 1 plus 2 times k plus 1, the quantity, all over 2. Okay, so we do have a common binomial factor, namely k plus 1. We can factor that out and we get k plus 1 Okay. Okay, k+1 on k. And so right here we have k here. Then we factor the k+1 out of this, and so we have k+2. And of course it's all still over the common denominator of 2. Well, let's see, I think that's what we were trying to prove, right? Yeah, we're trying to show that that was equal to that. And we did. And so we can write down QED, quandam est demonstrandum, thus we have demonstrated, or something like that in Latin. Okay, and that finishes it, folks. Okay, and I kind of like this problem. It's I've been studying the arithmetic functions like phi and the Euler phi function, the tau function. There's others, I think. The sum of the divisors, all of that, you know, and they're kind of connected in a way. There's relationships between them that's kind of interesting that I've been studying. But anyway, I hope you enjoyed that. We define an arithmetic function via a summation with a slightly unusual looking summation symbol. It's just a condition on n determines the sum ends, the elements that you input into the tau function. All right. Thanks for viewing.